In precisely 48 hours, an extraordinary event is set to unfold, the culmination of quiet preparations by NASA. An object, traversing space at a velocity of 137,000 miles per hour, originating from a star system beyond our own, will narrowly miss Mars, passing within 29 million kilometers. However, a critical detail has been omitted from public discourse. Loeb, a distinguished figure from Harvard, has assigned this celestial body a rating of 6 out of 10 on his scale for the likelihood of possessing alien technology, indicating a 60% probability that its nature is not organic. The subsequent photographic evidence captured by amateur astronomers is poised to throw the scientific community into considerable disarray, as this entity is exhibiting behavior utterly unlike any comet ever observed. It is emitting pure nickel without any trace of iron, a phenomenon deemed impossible in natural celestial processes, yet a hallmark of industrial fabrication. Its chemical composition is 16 times more extreme than that of any known comet, and it transformed from a reddish hue to green practically overnight. Furthermore, its trajectory possesses only a 1 in 500 chance of being a random occurrence. The situation intensifies with a chilling revelation. In late September, the object designated Three-Eyed Atlas will vanish behind the Sun for a period of 2 months, rendering it invisible to us during its closest approach to Mars on October 30th. Loeb posits that this concealment could be deliberate, a maneuver to evade observation during its brightest phase or to coincide with another undisclosed event. Some researchers hypothesize that it may have already released undetectable precursor probes, too minute for terrestrial telescopes to discern, which could potentially reach Mars while our attention is focused on the primary object. Over 227 observatories globally have been tracking this phenomenon, accumulating more than 4,000 observations, each piece of data further deepening the enigma. With a calculated mass of 33 billion tons, its existence defies conventional understanding. The mathematical models do not align with expected outcomes. Based on current cosmological models, we should have encountered 100,000 smaller objects prior to discovering something of this magnitude. Therefore, the question remains, what precisely is Three-Eyed Atlas? In the ensuing hour, we will delve into every observed anomaly, every leaked observation, and every theory that scientists are hesitant to openly discuss. The reason for this forthcoming revelation is that following October 3rd, when the Martian spacecraft redirect their instruments towards this object, we may finally obtain answers. Alternatively, we might encounter something far more unsettling. If this mystery captivates you as much as it does me, please indicate your engagement by liking this content and subscribing. I invite you to share in the comments section your current location, the local time, and the most peculiar incident you have ever experienced. Chapter 1. Avi's Remarkable 6 out of 10 Assessment. Avi Loeb has recently undertaken an action that is sending ripples of astonishment throughout the field of astronomy. The Harvard astrophysicist, who previously suggested in 2017 that oumuamua might be indicative of alien technology, has now evaluated Three-Eyed Atlas with a 6 out of 10 rating on his scale, assessing the probability of technological origins. This signifies a 60% conviction that the object is not naturally occurring. Before dismissing this assertion, it is crucial to comprehend the basis for his revised assessment. This conclusion is not rooted in mere speculation, but rather in empirical data gathered by the James Webb Space Telescope, the Very Large Telescope in Chile, and the Hubble Space Telescope, all of which have revealed characteristics that defy current scientific understanding. The James Webb Telescope observed Three-Eyed Atlas on August 6th and determined that its gaseous plume comprised 95% carbon dioxide and a mere 5% water. This composition is 16 times more extreme than that of any known comet at comparable distances from the Sun, as comets are typically water-rich, a characteristic notably absent in this instance. Subsequently, the Very Large Telescope detected nickel within the gas plume, evidenced by strong, unambiguous emission lines. However, the most astonishing finding was the complete absence of iron. Across the entire history of astronomical observations, nickel and iron have invariably been detected together. They are jointly synthesized within dying stars and dispersed together during supernova events. The discovery of nickel without iron is akin to observing smoke without a fire. It is a phenomenon that does not occur in nature, but is commonplace in industrial manufacturing, specifically in the production of high-purity nickel alloys and aerospace components. The chemical signature precisely matches that of factory production rather than that of cosmic debris. Furthermore, the rate of nickel production is escalating. When initially detected in July, the emission rate was moderate, but by August, it had increased dramatically by a factor of 25. As the object draws nearer to the Sun, it appears to be vaporizing a greater quantity of metal. Loeb has faced considerable professional censure for even contemplating extraterrestrial explanations for such phenomena. Jason Wright of Penn State University characterized his work as careless, and Tom Statler of NASA maintained that the object exhibits characteristics consistent with a comet performing typical cometary functions. However, neither critic has offered an explanation for the presence of nickel in the absence of iron, nor have they addressed the exceptionally high carbon dioxide ratio or the trajectory that possesses a mere 1 in 500 probability of being coincidental. Loeb himself acknowledges that his technological hypothesis is largely an exploratory exercise, conceding that a natural comet remains the most probable explanation. Nevertheless, most probable does not equate to certainty. His 6 out of 10 rating implies a 40% likelihood that our current assumptions are fundamentally flawed. The flyby of Mars on October 3rd is anticipated to provide further clarity. If the high-resolution imaging science experiment, HiRISE, camera reveals a nucleus exceeding 5 kilometers in diameter, as suggested by his mass calculations, then the natural explanation would be definitively invalidated. The quantity of rocky material available in interstellar space is insufficient to account for the frequent appearance of such large objects. Chapter 2. The amateur photograph that captivated the internet. Social media platforms are currently abuzz with observations that professional astronomers are conspicuously avoiding. Amateur astrophotographers are disseminating images of three-eyed Atlas that deviate significantly from the expected appearance of a comet. Instead of the diffuse, fuzzy glow typically associated with comets, some photographs exhibit discernible structure, geometric patterns, and sharp edges that should not be present. Michael Jagger and Gerald Raymond, two highly regarded amateur astronomers, managed to capture images of three-eyed Atlas during the total lunar eclipse on September 7th from their observation point in Namibia. Their photographs depicted the object emitting a green luminescence with a bluish tint, clearly indicating a rich gas content and visibility across both blue and green filters. While professional astronomers have acknowledged the authenticity of these specific images, it is the contributions of other amateur enthusiasts, whose names have not been widely publicized, that have produced what is now being referred to as the structured images. These photographs, circulating across Reddit, Twitter, and various astronomy forums, suggest a more solid, defined entity beneath the gaseous envelope, an object with distinct outlines rather than a diffuse cloud. The professional response to these images has been characterized by either silence or outright dismissal. When pressed for an explanation, professionals cite factors such as motion blur, exposure artifacts, and telescope tracking inaccuracies, all valid technical concerns when photographing rapidly moving celestial bodies that are thousands of times fainter than what the naked eye can perceive. Smearing and distortion are indeed common issues. However, what renders this situation particularly intriguing is the disparity in equipment. The Atlas Survey telescope that initially discovered three-eyed Atlas is a modest 20-inch instrument, comparable in size to equipment used by amateur astronomers. High-end hobbyists often possess equivalent or superior observational gear. Therefore, when an individual utilizing similar equipment captures images displaying unusual structural details, why is there an automatic dismissal without thorough investigation? On Reddit's astronomy subreddits, heated debates are unfolding. Users are meticulously comparing images side by side. Some exhibit the classic cometary appearance, complete with a developing coma and a faint tail. Others present phenomena that are considerably more challenging to explain. Compact nuclei, irregular shapes, and pixel patterns inconsistent with the standard point spread functions for stars or comets. A segment of commenters attributes these discrepancies to image processing errors, while another vehemently demands that professionals with advanced equipment replicate the observations to either confirm or refute the findings. This replication, however, is not materializing. Instead, professional astronomers are intervening in online discussions to discredit these images without offering to conduct their own verification. One image widely circulated on X appears to showcase a more compact and less diffuse core than what was captured by the Hubble Space Telescope. The amateur who posted it claimed it was obtained using a 14-inch Schmidt-Cassegrain telescope and was a composite of 50 individual exposures, a standard practice for deep sky imaging. Professional astronomers swiftly attributed the perceived anomaly to atmospheric distortion, tracking drift, or chromatic aberration, any plausible explanation to dismiss the observation. Yet, crucially, none of them proposed directing larger telescopes toward the same celestial coordinates or offered assistance in verifying the amateur's findings, opting instead for immediate dismissal. The situation becomes even stranger when considering the Hubble Space Telescope's image from July 21st, which revealed a teardrop-shaped dust cocoon with its glow emanating forward towards the sun. This official NASA data already defied expectations, as cometary tails are conventionally understood to stream behind the object, propelled by solar wind and radiation pressure. This particular object, however, was oriented forward. Professional astronomers describe this anomaly as interesting, puzzling, and worthy of study. When amateurs observe peculiar phenomena during the same time frame, it is promptly labeled as user error. Subsequently, observations from the Gemini South Telescope on August 27 provided the initial evidence of a conventional anti-solar tail extending behind the object. This suggests that between July and August, a significant change occurred. Either three-eyed Atlas began behaving more like a traditional comet, or our vantage point shifted sufficiently to reveal characteristics that were present all along. It is noteworthy that the majority of amateur photographs depicting unusual structure were taken during this July to August window, a period when the object exhibited the least cometary behavior, and even professional observations revealed anomalies. An additional piece of data that warrants greater attention comes from NASA's Spitzer Infrared Space Telescope, which observed three-eyed Atlas in early August. It appeared as a distinct point source, devoid of an extended coma or tail, simply a single bright. This is not how comets typically appear in infrared imagery. They usually display extended emission from warmed gas and dust. However, Spitzer detected nothing of this nature, only a solitary point of light. Thus, a discernible pattern emerges. Professionals are observing anomalies they cannot fully elucidate, while amateurs are observing anomalies that are dismissed as technical incompetence. Both are photographing the same celestial body during the same peculiar interval when its behavior deviated from that of a typical comet. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter are scheduled to photograph three-eyed Atlas on October 3rd, utilizing cameras designed to image the Martian surface from distances of mere hundreds of kilometers. These instruments will be observing this object from a distance of 30 million kilometers. The ESA has already stated that spectacular images are not anticipated, as the object will likely appear as less than a single pixel in their camera's resolution. However, what if the amateur observations were accurate? What if there is indeed structure present beneath the gaseous envelope? The October observations may not provide definitive resolution either. It is possible that a closer approach, coupled with more advanced instrumentation precisely aimed at this object and free from atmospheric interference, will be required. The reality is that we are operating with incomplete information. Professional telescopes have limited observation time and adhere to strict schedules. Amateurs possess greater flexibility but employ less sophisticated equipment. Somewhere within this observational gap, something unusual is occurring that neither party is entirely willing to acknowledge. This is because if the amateurs are indeed correct, and if there is structural evidence that does not conform to the morphology of natural comets, then we are no longer discussing imaging artifacts. We are confronting the necessity of revising our fundamental understanding of interstellar visitors. Chapter 3. The October 3rd Mars Encounter. What they are not disclosing. In 2 days, three-eyed Atlas will pass within 29 million kilometers of Mars. While this may seem like a considerable distance, the critical aspect that is not being widely discussed is the minimum orbit intersection distance. This represents the closest proximity the object will achieve to Mars' complete orbital path around the Sun, a mere 2.7 million kilometers. Loeb has described this proximity as remarkable fine-tuning, a phrase that warrants significant attention when uttered by a Harvard physicist. The high-rise camera aboard the Mars Reconnaissance Orbiter is equipped to image three-eyed Atlas with a resolution of 30 kilometers per pixel on October 3rd. This level of detail is sufficient to distinguish the nucleus from its surrounding dust cloud, to measure the actual surface area reflecting sunlight, and to definitively ascertain whether this object truly measures 5 kilometers across, as suggested by Loeb's latest mass calculations. If its dimensions are indeed that substantial, the natural comet explanation would be entirely invalidated. Based on the limited reservoir of rocky material believed to exist in interstellar space, we would have anticipated detecting approximately 100,000 smaller interstellar objects, similar in scale to oumuamua, before encountering something as massive as three-eyed Atlas. Yet, we have only identified 2 prior interstellar visitors, both considerably smaller than this current object. However, the situation takes a genuinely disturbing turn when considering a calculated possibility by Loeb. He posits that if three-eyed Atlas were to deploy a precursor probe, a smaller scouting craft traveling approximately 30 million kilometers ahead of the main object, such a probe could intercept Mars on October 3rd or during the preceding week. The alarming aspect of this scenario is that Earth-based telescopes are incapable of detecting objects smaller than approximately 100 meters at Martian distances. This size threshold is roughly equivalent to the largest spacecraft ever launched by humanity. Consequently, any precursor probe would be effectively invisible to our current observational capabilities. This concept is not as far-fetched as it may initially seem. If one were designing an interstellar mission to survey a planetary system, the logical approach would not be to dispatch a single, massive vessel. Instead, a mothership accompanied by smaller reconnaissance probes would be deployed ahead to gather data on individual planets, while the primary craft maintains a safe trajectory through the system. This mirrors precisely how such a mission would be designed if the necessary technology were available. Furthermore, the trajectory of Three-Eyed Atlas renders this scenario disturbingly plausible. The object's path would necessitate only a minor velocity adjustment, between 10 and 15 kilometers per second, during September to reduce its closest approach distance to Mars to zero. For a technologically advanced object, this maneuver would be trivial. For a natural comet, it is virtually impossible. The ejection velocity of icy fragments from sublimating comets, as indicated by data from the James Webb Telescope, is only around 0.4 kilometers per second, which is insufficient for such a trajectory alteration. NASA's Mars Express and ExoMars Trace Gas Orbiter will also be engaged in observing Three-Eyed Atlas on October 3rd, utilizing multiple instruments, including high-resolution cameras, spectrometers, and particle sensors. Although these instruments are primarily designed for studying the Martian surface and atmosphere, they are being repurposed to examine this interstellar visitor. Their objective will be to characterize the comet's volatile activity and composition from a distance of 30 million kilometers. However, there exists a secondary objective that is not being publicly advertised. The Mars Reconnaissance Orbiter will not solely image Three-Eyed Atlas. It will also scan the surrounding space for any objects potentially traveling ahead of the main body, searching for precursor probes. Loeb explicitly suggested this possibility in his published works, advocating for the use of HiRISE to search for objects preceding Three-Eyed Atlas that might approach Mars more closely than the primary object. If materials originating from Three-Eyed Atlas reach Mars in October, materials that could not have naturally arrived through sublimation and ejection, this would constitute a definitive signature of technology. The timing of these events is also highly suspicious. Three-Eyed Atlas achieves its closest approach to Mars exactly 1 week before it disappears from Earth's perspective due to its passage behind the Sun. This provides us with a single opportunity for detailed observation by spacecraft at Mars, after which the object will vanish into solar glare for 2 months, remaining unobservable until early December. This temporal window would be ideal for deploying a probe to Mars undetected, specifically during the October 3rd flyby, while Earth-based telescopes are focused on the primary object. Subsequently, the mothership could conceal itself behind the Sun for 8 weeks while the probe carries out its undisclosed mission. NASA's Curiosity and Perseverance rovers, situated on the Martian surface, may also attempt observations. Although the comet will appear incredibly faint from the surface perspective, the Mars Reconnaissance Orbiter represents our most promising avenue for detailed imaging. Compounding these concerns is the question of what actions would be taken if something significant were discovered. If HiRISE captures an image revealing multiple objects, anomalous maneuvering, or any indication of artificial activity, what would be the established protocol? Would the findings be announced immediately? Would they undergo verification through additional observations? Or would they be classified? There is no established procedure for such a scenario because no one has seriously prepared for it. Existing protocols for detecting extraterrestrial intelligence primarily focus on radio signals or optical beacons, not the physical transit of craft through the inner solar system. Within 24 hours, we will ascertain whether the amateur astronomer's observations hold validity. We will learn whether the nickel without iron signature carries the implications that Loeb suggests. We will determine whether the 2.7 million kilometer minimum orbit intersection distance is a coincidence or a deliberate design. Alternatively, we may witness the passage of a perfectly ordinary comet nucleus consistent with natural formation, causing all speculation to dissolve into collective embarrassment. Regardless of the outcome, October 3rd, 2025, is a date that may well be etched into history books. The day on which we either confirm Three-Eyed Atlas as an extraordinary but natural interstellar comet, or the day when everything we thought we knew changes irrevocably. Chapter 4. The Nickel Without Iron Revelation. The Very Large Telescope in Chile has detected a phenomenon that defies natural explanation. Between late July and late August of 2025, spectroscopic analyses revealed the presence of neutral nickel atoms emanating from Three-Eyed Atlas. These emissions were observed as strong lines at multiple wavelengths, providing clear and unambiguous evidence of nickel sublimating from the object's surface as it approached the Sun. Crucially, no iron was detected whatsoever. Not a single emission line appeared at any of the expected wavelengths where iron should be present. To fully grasp the magnitude of this discovery, it is essential to understand a fundamental principle. Nickel and iron are cosmic twins. They are forged simultaneously through the same nuclear reactions within massive stars. When these stars subsequently explode as supernovas, nickel and iron are ejected together into space, where they condense into dust grains, and become incorporated into asteroids and comets as a combined entity. In every single space rock that humanity has ever analyzed, from meteorites that have landed on Earth to samples returned from space missions, nickel and iron appear in predictable ratios. The discovery of one element without the other would be akin to finding hydrogen devoid of protons. It fundamentally challenges the established chemistry of the universe. The research team at the Very Large Telescope, comprising scientists independent of Avi Loeb's more controversial theories, published their findings with carefully worded conclusions. They proposed that the nickel might originate from nickel-carbonyl compounds, molecules that, in theory, could exist in extremely cold interstellar environments. These compounds are volatile and are expected to break down when exposed to ultraviolet light, releasing nickel and carbon monoxide. However, even the Very Large Telescope team acknowledged that this scenario would be unprecedented, never having been observed in any comets within our solar system or detected in interstellar space. It represents a purely theoretical explanation for an observation that strongly suggests such a phenomenon. The situation is further compounded by the fact that the nickel production is not constant. When Three-Eyed Atlas was first observed at a distance of 3.9 astronomical units from the Sun in July, the nickel emission rate was approximately 10 to the power of 21. While significant, this was not yet alarming. By late August, when the object was at 2.85 astronomical units, that rate had increased by a factor of 25, meaning 25 times more nickel was streaming from the object's surface in just 1 month. The closer the object gets to the Sun, the more dramatically its metal emissions intensify. This increase does not follow the gradual curves characteristic of normal cometary outgassing. Instead, it exhibits an exponential, steep rise, suggesting a process of systematic vaporization driven by increasing heat. Avi Loeb highlighted a critical point that others have been reluctant to explicitly state. On Earth, nickel is routinely separated from iron in industrial processes. High-purity nickel is utilized in specialized alloys for applications in aerospace, electronics, and batteries, wherever specific thermal or electromagnetic properties are required. The signature detected from Three-Eyed Atlas is consistent with industrial nickel production, not with natural cosmic abundances. Critics were quick to dismiss this observation, alleging that Loeb was selectively presenting data, pursuing a predetermined conclusion, and engaging in motivated reasoning. Jason Wright of Penn State was particularly harsh, deeming the comparison to industrial processes to be misleading and unscientific. However, the critics have failed to address a crucial point. If the nickel is indeed originating from natural carbonyl compounds, then where is the iron? Iron forms similar volatile compounds. Iron pentacarbonyl, for instance, is a well-studied substance in chemistry. If the conditions were suitable for the creation and preservation of nickel carbonyl throughout billions of years in interstellar space, then identical conditions would have facilitated the creation of iron carbonyls. Both should be present, yet only nickel is being detected. The Very Large Telescope observations also revealed a rapid increase in cyanide production. Hydrogen cyanide and related compounds were detected in the gas plume surrounding Three-Eyed Atlas at rates that escalated sharply as the object approached the Sun. Loeb suggested that the observed color change from red to green, noted by amateur astronomers, might be connected to this surge in cyanide levels. While cyanide itself is not uncommon in comets, being a frequent carbon and nitrogen compound found in many icy bodies, the rate of its increase, and its steep production curve mirroring the nickel emissions, strongly implies a linked process. What's truly remarkable is what this reveals about the object's internal makeup. If the majority of its substance is comprised of frozen carbon dioxide, with only minute traces of water, as Mr. Webb observed, and if the outer layer is releasing nickel and cyanide at escalating rates, then we are confronted with a chemical profile unlike anything formed within our solar system. Comets originating from the Oort cloud or the Kuiper belt are abundant in water, as they coalesced in an environment where water ice remained stable. The proportion of water to carbon dioxide reflects the thermal conditions and composition of the primordial disk from which they emerged. Three-Eyed Atlas exhibits the inverse ratio. It is predominantly carbon dioxide with negligible water. This indicates it originated in a vastly different setting, perhaps around a dissimilar star. Alternatively, it suggests the object is not a natural phenomenon at all. A third possibility exists, one that few are willing to seriously consider. What if Three-Eyed Atlas is indeed naturally formed, an ancient comet from another star system, but its surface chemistry has been profoundly altered by its prolonged journey through interstellar space? Exposure to cosmic radiation, collisions with interstellar dust particles, and chemical reactions in the near-absolute zero vacuum over 7 billion years could induce peculiar changes in its surface composition. It's conceivable that the signature of nickel without iron is accurate, but the explanation lies somewhere between a natural comet and an engineered vessel. something we haven't yet conceived because we've never examined an object of such age from such a remote distance. The observations planned for October will be invaluable when the high-resolution imaging science experiment, HiRISE, captures images of 3I Atlas from Martian orbit. Spectroscopic data from the Mars Express and ExoMars Trace Gas Orbiter missions will detect additional emission lines, providing more information about nickel production, further measurements of cyanide and carbon dioxide outgassing, and more definitive clues about the object's true nature. However, based on the current data, 3I Atlas is expelling industrial-grade nickel into space while exhibiting no discernible iron. And no one has a satisfactory natural explanation for this phenomenon. Chapter 5. The Vanishing Act, Concealed by the Sun. In late September, 3I Atlas disappears from view, not through destruction or deflection, but simply by becoming obscured. From Earth's vantage point, it passes too close to the Sun to be observed. For a period of 2 months, from late September through November, ground-based telescopes lose all line of sight. The object is lost in the blinding glare of the Sun. What makes this timing particularly suspect is that 3I Atlas reaches perihelion, its closest approach to the Sun, on October 30th, 2025. This is the juncture when comets are most active, when solar heating triggers maximum outgassing, and when their behavior offers the most profound insights into their composition and structure, arguably the most crucial observational window for understanding the object's true identity. Yet, at this critical time, we cannot see it. Earth will be positioned on the opposite side of the Sun. Loeb proposed that this alignment might not be coincidental, but rather a deliberate maneuver, not random orbital mechanics. If 3I Atlas aimed to evade detailed scrutiny from Earth-based telescopes during its brightest and most active phase, its current trajectory achieves precisely that, hiding behind approximately 150 million kilometers of incandescent plasma at the pivotal moment. NASA and other space agencies are attempting to circumvent this observational blackout. The Parker Solar Probe, currently in a close solar orbit studying the Sun's corona, might capture a fleeting glimpse if its timing happens to align. The Solar and Heliospheric Observatory, SOHO, which continuously monitors the Sun for coronal mass ejections, will have 3I Atlas traverse its field of view. However, SOHO's cameras are designed for solar observation, not for detecting faint comets. The object will likely be too dim against the overwhelming brilliance of the Sun. The Jupiter Icy Moons Explorer, JUICE, is presently on the far side of the Sun relative to Earth. It is utilizing its high-gain antenna as a heat shield, which restricts its data transmission capabilities. JUICE will attempt observations of 3I Atlas in November, employing its cameras and spectrometers, but the data will not be received until February 2026, months after the observations are made. Consequently, we are effectively blinded during the most critical period, with October 30th passing behind a celestial curtain. And what could transpire during those 2 months? If 3I Atlas is a natural object, nothing unexpected should occur. It will heat up, outgas more intensely, possibly fragment if thermal stress causes the nucleus to fracture, and then re-emerge in December, slightly diminished in size and activity, as it continues its journey back into interstellar space. However, if it is not natural, if any technological component is involved, those 2 months represent an ideal window for activities we are not meant to witness: orbital adjustments, probe deployments, trajectory modifications, any maneuvers requiring propulsion or spatial navigation that would be evident to Earth-based observers if we could see them. Loeb calculated that even a modest change in velocity of 10 to 15 kilometers per second during September or October could significantly alter 3I Atlas's trajectory, sufficient to divert payloads to Mars, Venus, or even Earth. For a natural comet, such a feat is impossible. Sublimating ice generates velocity impulses of perhaps half a kilometer per second at most. But for an object equipped with an engine, this is a trivial matter. A more unsettling possibility exists. What if the disappearing act is precisely that? What if 3I Atlas does not reappear in December? What if it leverages its perihelion passage to shed velocity, entering a long, elliptical orbit around the Sun, thereby becoming a permanent inhabitant of the inner solar system? We would have no means of knowing until December, when it is expected to reemerge. And if it fails to manifest at the predicted location, if its orbit has undergone substantial alteration, that would serve as a definitive indicator of propulsion, of technology, of intent. There is historical precedent for such reasoning, though not involving interstellar objects. In 1986, the Soviet Vega probes flew past Halley's Comet and detected something unanticipated. The nucleus was far darker than anticipated, reflecting merely 4% of the incident sunlight. Prior to the Vega missions, scientists presumed comets to be bright, icy bodies. It transpired that they are exceptionally dark, coated in organic compounds and dust. with the ice concealed beneath a crusty surface layer. That discovery fundamentally changed our perception of what comets look like up close. And it occurred because we dispatched spacecraft to investigate. Remote observation from Earth had led to entirely erroneous assumptions. With 3I Atlas, we are once again relying on remote observation during this critical period, inferring behavior from limited data and forming assumptions that could be completely flawed. We will not know the truth until December 3rd, when it emerges from behind the Sun and becomes visible again to ground-based telescopes. Amateur astronomers are already preparing. Telescopes across the globe are being scheduled for early December observations. Everyone is eager to be the first to spot its return. Everyone wants to ascertain if it appears different, if its activity level has changed, or if its trajectory aligns with predictions. Because if it deviates, if 3I Atlas emerges from perihelion on an altered path or with modified characteristics, it will compel the mainstream astronomical community to seriously consider the artificial hypothesis, not as a fringe theory championed by a single controversial scientist, but as a legitimate possibility demanding thorough investigation. The disappearing act also means we miss potential fragmentation events. Natural comets occasionally break apart near perihelion. Thermal stress causes fractures in the nucleus. Internal pressure from trapped volatiles propels fragments from the surface. We have witnessed this phenomenon with several comets that ventured too close to the Sun. If 3I Atlas fragments, we will not observe the event itself. We will only see the aftermath in December. Multiple pieces instead of one, trails of debris, altered rotation. Fragmentation would, in fact, support the natural comet hypothesis. Technological objects do not typically disintegrate due to solar heating. Unless the fragmentation is controlled, unless what we perceive as breakup is actually a deliberate deployment, with smaller objects separating from the main body, each proceeding toward different destinations within the inner solar system. Such a scenario sounds like science fiction, but so does the presence of nickel without iron. So does the precise alignment with the ecliptic plane. So does the flyby of Mars with an accuracy of 2.7 million kilometers. Each piece of data we gather renders the science fiction scenarios slightly less fantastical. The emergence in December will reveal something. Perhaps not everything, but something. And until then, we wait in uncertainty, hoping that the object that reappears is the same one that vanished behind the Sun. Chapter 6. The anomalously massive object, 33 billion tons. A new research paper has been published, causing significant unease among astronomers. Richard Chloe, Peter V.E., and Avi Loeb analyzed 4,022 observations of 3I Atlas, collected from 227 observatories worldwide between May 15th and September 23rd. They meticulously tracked the object's position, comparing its actual trajectory to what would be predicted by gravitational forces alone. Their findings were startling. 3I Atlas exhibits almost no non-gravitational acceleration. Despite extensive outgassing detected by the James Webb Space Telescope and other observatories, and despite losing hundreds of kilograms of material per second, the object's trajectory deviates by less than 15 meters per second squared from a purely gravity-driven path. This implies an extraordinarily high mass, far exceeding what its luminosity would suggest. The mathematical reasoning is straightforward. When a comet releases gas, the expelled material acts like a minuscule rocket engine, imparting a slight push that nudges the comet off course. The magnitude of this deviation depends on the rate of mass expulsion and the total mass of the comet. Small comets with vigorous outgassing display significant non-gravitational acceleration. Larger comets with comparable outgassing exhibit less deviation. 3I Atlas is expelling vast quantities of gas. The James Webb Space Telescope measured 129 kilograms per second of carbon dioxide, 6.6 kilograms per second of water, and 14 kilograms per second of carbon monoxide. These are substantial rates, which should produce noticeable trajectory changes. However, they do not. The deviation remains below detection limits, indicating that the object's mass must be immense to counteract the propulsive effect. Calculations place the lower limit at 33 billion tons, or 33 trillion kilograms, with a nucleus diameter of at least 5 kilometers. This renders 3I Atlas 3 to 5 orders of magnitude more massive than the two preceding interstellar objects. Oumuamua was perhaps a few hundred meters across at most, and Borisov was approximately 1 kilometer. This object is 5 times larger in diameter, translating to over 100 times the volume and mass. The critical issue is this. Based on our current understanding of interstellar space and surveys of the abundance of rocky and icy material between stars, objects of this magnitude should be exceedingly rare. So rare, in fact, that we would expect to detect roughly 100,000 smaller interstellar visitors before encountering one as massive as 3I Atlas. Yet, we have identified only 2 such objects throughout human history. It's akin to winning the lottery 3 consecutive times, statistically possible, but so improbable that one begins to question the integrity of the game. Loeb posits that this suggests a non-random trajectory. If 3I Atlas was intentionally directed toward the inner solar system, if its path was a deliberate choice rather than a random occurrence, then the statistical anomaly dissolves. We are not sampling the interstellar population at random. We are being visited by something specific. Critics dismiss this as preposterous. They point to the dramatic improvements in our detection capabilities in recent years. The Atlas survey, which discovered 3I Atlas, only became fully operational within the last decade. Previously, our observational efforts were insufficient. It is therefore unsurprising that we are now finding more interstellar objects. We finally possess telescopes capable of detecting them. This is a valid argument. The Vera C. Rubin Observatory, commissioned in 2025, identified over 2,000 asteroids within its initial 10 hours of operation. Our capacity to detect faint, rapidly moving objects has expanded exponentially. It is plausible that we will discover dozens more interstellar visitors in the coming years, thereby resolving the statistical problem. However, this does not account for the mass. Even with enhanced detection and the discovery of more interstellar objects, the size distribution should conform to predictions: a preponderance of small objects, fewer medium-sized ones, and very few large ones. This is how populations typically function in astronomy. Small asteroids vastly outnumber large ones, by millions to one. 3I Atlas defies this pattern. It is by far the largest object we have found, discovered before we have cataloged the thousands of smaller objects that should be more common. Furthermore, the absence of significant non-gravitational acceleration precludes certain explanations. Some scientists have suggested that 3I Atlas might be a loosely aggregated collection of debris held together by weak gravitational forces. If this were the case, outgassing would cause it to disintegrate. The propulsive forces would overcome the gravitational binding, leading to fragmentation. Yet, it is not fragmenting. It remains cohesive despite substantial mass loss. This necessitates either a solid, integrated nucleus or a binding mechanism more potent than self-gravity. The planned observations from Mars in October may help clarify the size of the object. If the HiRISE instrument can differentiate the nucleus from its surrounding dust cloud and quantify the light reflected from the solid surface versus scattered by particles, we will obtain a more precise estimate of the nucleus's true diameter. If it exceeds 5 kilometers, the natural explanation becomes untenable. Another possibility, which has received less attention, is that 3I Atlas is enveloped by a vast, diffuse cloud of extremely fine dust, and the majority of the observed brightness originates from this dust rather than the nucleus itself. In this scenario, the nucleus could be significantly smaller, and the mass calculations would be erroneous. However, observations by the James Webb Space Telescope and the Spitzer Space Telescope, assuming Sphere X refers to a similar infrared observatory, were conducted in the infrared spectrum. Infrared light penetrates dust, revealing solid surfaces beneath. Sphere X detected 3I Atlas as a point source, not an extended cloud. This suggests that there is no massive dust envelope obscuring a small nucleus. What we are observing is primarily the object itself. Therefore, we are left with a 5-kilometer nucleus possessing at least 33 billion tons of mass, exhibiting almost no non-gravitational acceleration despite considerable outgassing. This is an object that, statistically speaking, should not exist. It arrived on a trajectory with only a 1 in 500 chance of being random. The accumulating data continues to challenge the natural explanation, rendering it increasingly contrived and reliant on numerous coincidences and unprecedented circumstances. Chapter 7. Chemical Impossibilities, the 95% CO Mystery. The James Webb Space Telescope observed 3I Atlas on August 6, 2025, utilizing its near-infrared spectrograph. The findings have prompted a re-evaluation of our understanding of what interstellar comets should resemble. The gaseous plume surrounding 3I Atlas comprises 95% carbon dioxide and merely 5% water. This ratio is 16 times more extreme than anticipated for a typical comet at that distance from the Sun. Every comet we have ever studied from our solar system is water-rich. They formed in the frigid outer regions where water ice was the predominant volatile compound. Carbon dioxide is present, but in significantly smaller quantities. This ratio reflects the temperature and chemistry of the protoplanetary disk where they originated. 3I Atlas exhibits an inverted chemistry. It is essentially a dry ice ball with very little water. This indicates that it formed in a fundamentally different environment, perhaps around a star with a distinct elemental composition, within a disk subject to different temperatures and pressures, in conditions unlike those that shaped our own solar system. Martin Cordiner, the principal investigator for the James Webb Space Telescope observations, stated, This is among the highest carbon dioxide to water ratios ever measured in any comet. Not just unusual, but unprecedented. However, the chemical peculiarities extend further. The James Webb Space Telescope also detected significant quantities of carbon monoxide and carbonyl sulfide. The presence of these compounds in combination suggests that the object originated in an extremely cold environment, potentially colder than the outermost reaches of our solar system. Some researchers propose that 3I Atlas might have originated in a molecular cloud region or been ejected from a planetary system located much farther from its star than our Kuiper belt. Then there is the color alteration documented by amateur astronomers. In July and early August, observations indicated that 3I Atlas possessed a reddish coma. This color is typically indicative of organic compounds, complex carbon molecules that absorb blue light and reflect red. This is standard for comets. However, on September 7th, during a total lunar eclipse, Michael Jagger and Gerald Raymond photographed it glowing a vivid green with a bluish tinge. This transformation occurred seemingly overnight. Green comets are a well-known phenomenon. The color arises from diatomic carbon molecules in the coma absorbing ultraviolet sunlight and re-emitting it as green light. Yet, 3I Atlas had already been analyzed in August by astronomers at the Kitt Peak Observatory. They determined that it was among the comets with the lowest concentrations of carbon chains known. It exhibited very low levels of diatomic carbon, precisely the molecule responsible for producing green comets. So, how could a comet with virtually no diatomic carbon suddenly emit a brilliant green glow? Abbie Lowe suggested that the color change might be linked to the rapid increase in cyanide production detected by the Very Large Telescope. Cyanide compounds can also produce greenish hues under specific conditions. But this raises another question. Why is cyanide production escalating so dramatically? The Very Large Telescope observations indicated a steep rise in hydrogen cyanide emissions as 3I Atlas approached the Sun. The production rate was not gradual, as expected from typical cometary outgassing, but exponential, suggesting a process of thermal alteration occurring at accelerating rates. Stephanie Millam of NASA's Goddard Space Flight Center, who participated in the James Webb Space Telescope observations, theorized that 3I Atlas might possess a cooked outer shell. Billions of years of travel through interstellar space, exposure to cosmic rays and stellar radiation, could have chemically altered its surface layers. Carbon dioxide might have been created or concentrated through these processes, resulting in its unusual surface chemistry. This is a plausible hypothesis. We have never examined an object of such antiquity. 7 billion years predates our entire solar system. It is difficult to fathom what might happen to ice over such a timescale in the near absolute zero void between stars. However, this explanation does not account for everything. The signature of nickel without iron is not explained by surface processing, nor is the lack of significant outgassing. Each anomaly might possess a natural explanation independently, but taken together, they form a pattern that becomes increasingly difficult to dismiss. Furthermore, the Spitzer Space Telescope observation revealed 3I Atlas as a point source with no extended emission. Infrared telescopes can penetrate dust to reveal the thermal radiation emanating from warming ice and rock. The Spitzer telescope should have detected a broad, diffuse glow from carbon dioxide ice sublimating across the surface. Instead, it registered a distinct point, a concentrated source of infrared emission consistent with a relatively compact solid object. This observation contradicts the conventional model of a comet. Alternatively, it suggests the object possesses highly unusual thermal properties. Perhaps its surface is exceptionally reflective, deflecting sunlight before it can heat the interior. Possibly, an insulating layer prevents heat penetration. Or maybe the nucleus is spinning so rapidly that thermal energy is dispersed before significant sublimation can occur. Or, it is possible that it is not outgassing in the manner we assume. Perhaps what we interpret as sublimation is something entirely different. The chemical data also provides insights into 3I Atlas's potential origin. Its low metallicity and high hydrogen and ice content suggest it originated from a region of the galaxy where star formation occurred early, the thick disk of the Milky Way, populated by older stars with less enrichment in heavy elements. Models propose its origin lies between 7 and 11 billion years in the past, marking it as a remnant from an era when our galaxy was vastly different. If 3 Atlas is indeed a natural phenomenon, it represents a time capsule from an ancient galactic epoch. It's a fragment of primordial ice carrying chemical imprints from billions of years prior to Earth's formation. This alone would elevate it to the status of the most scientifically significant object ever observed. However, its chemical composition consistently defies easy explanation. The prevalence of carbon dioxide can be accounted for. The scarcity of water is explainable. The presence of cyanide is also understandable, as is its changing color. Each individual characteristic possesses a plausible natural explanation, requiring only minor adjustments to our existing models, rather than a complete overhaul. It is the confluence of these anomalies within a single object that proves unsettling. The pattern of deviations, all appearing simultaneously in one entity, presents a statistical improbability concerning the chance occurrence of such a specific combination of traits. The months of November and December promise to yield additional data. As 3 Atlas reemerges from behind the Sun, ground-based observatories will capture new spectral analyses, revealing more emission lines, further chemical signatures, and providing more precise constraints on its composition. By contrasting its chemistry before and after its solar transit, we will ascertain whether solar heating has fundamentally altered any aspect of this object's behavior. Chapter 8 delves into the phenomenon of the anti-tail, a narrative that defies expectations. The Hubble Space Telescope acquired the most detailed image of 3 Atlas on July 21, 2025. What it depicted contradicted fundamental principles of cometary physics. The image revealed a teardrop-shaped envelope of dust, yet the illumination extended forward from the object towards the Sun. Conspicuously absent was a distinct tail streaming backward, away from the solar direction. This orientation is anomalous. Cometary tails are propelled away from the Sun by solar wind and radiation pressure, and should invariably point away from the Sun, creating the characteristic swept-back appearance associated with comets. However, 3 Atlas exhibited its brightest side facing forward, towards the Sun, with no discernible tail trailing behind. Loeb and his collaborator, Eric Kito, published the sole scientific paper attempting to account for this anti-tail. They posited that the forward radiance might be attributed to dust particles propelled ahead of the nucleus by some intrinsic process, though they acknowledged the speculative nature of this hypothesis. No clear mechanism has been identified that could naturally produce a forward-facing dust cloud on a conventional comet. Other astronomers disregarded the observation entirely, arguing that the glow was not an anti-tail, but rather a distortion caused by Hubble's tracking of the rapidly moving celestial body. The telescope was following 3 Atlas's movement through space, which could lead to streaks in the exposure from background stars. They suggested the forward illumination might be an artifact of this tracking motion. However, Hubble's image processing experts are adept at correcting for tracking effects. The streaks are readily apparent in the image, whereas the forward glow is not a streak, but a distinct area of heightened luminosity with discernible structure. If it were merely a tracking artifact, it would resemble the stellar trails. It does not. Subsequently, in late August, the Gemini South Telescope captured new images utilizing its multi-object spectrograph. Astonishingly, 3 Atlas had developed a conventional tail, a faint, teardrop-shaped appendage extending in the direction opposite to the Sun, precisely where cometary tails are expected to form. Therefore, between July 21 and August 27, a transformation occurred. Either the object began behaving like a typical comet, or our observational perspective shifted sufficiently to reveal what had always been present but obscured by the dust cloud. The July Hubble image was taken when 3 Atlas was approximately 4 astronomical units from the Sun. The August Gemini image was captured at roughly 2.6 astronomical units. Proximity to the Sun translates to increased solar heating, heightened outgassing, and potentially greater dust production. It is conceivable that the tail had not yet materialized in July and subsequently appeared as activity intensified. Nevertheless, this explanation does not account for the forward radiance. Typical comets do not display bright halos directed towards the Sun. They possess comas, which are spherical envelopes of gas and dust surrounding the nucleus. The coma can be brighter on the sunward side due to more vigorous sublimation, but it should not generate a directed glow ahead of the object's trajectory. Another perplexing detail in the Hubble image is the dust cocoon, which extends approximately 3,000 kilometers in all directions from 3 Atlas. Loeb calculated that if the nucleus is 10 kilometers in diameter, the dust density at 3,000 kilometers would be diminished by a factor of 90,000 compared to its density near the surface. This represents a substantial attenuation for such diffuse dust to remain sufficiently luminous for Hubble's detection. This implies either an immense volume of dust is being generated, or the dust particles possess exceptional reflectivity, or there is an unusual aspect to the scattering geometry. The Gemini images also indicated variations in color. Different wavelength filters revealed distinct structures. In the ultraviolet spectrum, the object appeared more condensed. In the red and infrared spectra, the dust cloud was more dispersed. This aligns with conventional dust scattering properties, where smaller particles scatter blue light more effectively and larger particles scatter red light. However, it also signifies that the size distribution of the dust grains is not uniform, with a population of very small particles close to the nucleus and larger particles farther away. This distribution pattern could provide insights into the ejection mechanism of the dust, suggesting fast-moving small particles and slower-moving large particles, characteristic behavior of comets. The complication arises from the object's rotation period. Observations indicated 3 Atlas rotates once every 16 hours, which is relatively slow for an object of its size. A 10-kilometer nucleus rotating every 16 hours has a surface velocity of merely about 1 meter per second at the equator, insufficient to expel dust particles into space through centrifugal force. Consequently, the dust must be ejected by gas pressure resulting from sublimation. Carbon dioxide sublimating from the sunward side carries dust grains along. However, analysis of the Hubble image suggested dust particles were moving at approximately 20 meters per second, significantly faster than the rotation speed, but consistent with gas drag. This is where the situation becomes particularly intriguing. If dust is being ejected at 20 meters per second by carbon dioxide outgassing, and if the object is losing 129 kilograms per second of carbon dioxide, as measured, then the dust production rate should be considerable, likely in the tons. Such a substantial quantity of dust ought to generate a highly conspicuous tail, a bright, extended plume visible in professional telescope imagery. Yet, the July Hubble image did not display one, only the forward glow and a diffuse coma. One possibility is that the dust particles are so minuscule that they are propelled forward by radiation pressure before they can coalesce into a traditional tail. Sunlight's radiation pressure can accelerate extremely fine dust grains more rapidly than gravity pulls them towards the sun. If the dust grain size is less than 1 micron, radiation pressure becomes the dominant force, potentially pushing the particles ahead of the nucleus. However, this would produce a forward tail, not a forward glow, rendering the morphology inconsistent. Another hypothesis is that the dust particles become electrically charged through exposure to solar ultraviolet radiation and interact with the sun's magnetic field. Electrically charged dust behaves differently from neutral dust and can be focused or dispersed by magnetic fields, leading to unusual configurations. NASA's SPEX observation adds another layer of complexity. It observed 3 Atlas as a point source in the infrared, devoid of any extended emission, no coma, no tail, merely a dot. Yet, Hubble clearly resolved extended structure. The discrepancy lies in the wavelengths observed. Hubble operated in visible light, while SPX focused on infrared. Dust reflects visible light, but emits thermal infrared radiation based on its temperature. If the dust surrounding 3 Atlas is exceedingly cold, colder than expected for its distance from the sun, it would appear faint in infrared even if bright in visible light. This suggests the dust is not efficiently absorbing solar heat. It might be highly reflective, bouncing light away before absorbing heat. Or it could be composed of materials with unusual thermal properties. The situation regarding the tail is expected to become clearer in December, when 3 Atlas reappears from behind the sun. New observations from multiple telescopes across a range of wavelengths will indicate whether the tail has grown further, whether it conforms to typical cometary tails, or if it continues to exhibit anomalous characteristics that deviate from established models. Chapter 9 examines the 1 in 500 trajectory coincidence. 3 Atlas is traversing a retrograde orbit, inclined at approximately 175 degrees relative to the ecliptic plane. While this sounds extreme, it essentially means the object is moving almost perfectly within the plane of the planets, but in the opposite direction. It is navigating the solar system along the same flat disk where Earth, Mars, Venus, and Jupiter orbit, but in reverse. The probability of this occurring randomly is estimated at 1 in 500. Most objects entering our solar system from interstellar space are expected to originate from random directions. Space is a three-dimensional expanse with no preferred orientation. If interstellar comets are merely debris ejected from other star systems on random trajectories, they should arrive from all angles, some from above the ecliptic plane, some from below, some from the sides, distributed uniformly across the celestial sphere. However, 3 Atlas entered the solar system with its trajectory almost perfectly aligned with the planetary orbits, deviating only 5 degrees from the ecliptic plane. While not impossible, this is highly improbable. Furthermore, it is not solely the inclination. The trajectory brings 3 Atlas into close proximity with multiple planets. It will pass within 30 million kilometers of Mars on October 3rd, approach Venus within a reasonable distance, and in March 2026, it will pass within 54 million kilometers of Jupiter. Each individual close encounter is not remarkable in itself. Space is vast, and many orbits pass near planets without intentional targeting. However, the combination of its alignment with the ecliptic and multiple planetary encounters significantly reduces the probability. Loeb calculated that the collective odds of all these geometric factors occurring by chance are approximately 1 in 500. This is not impossible, but it is sufficiently suspicious to warrant consideration of non-random explanations. If 3 Atlas were a deliberately sent probe for surveying the inner solar system, one would anticipate a trajectory that passes near the major planets and aligns with the ecliptic plane, as this is where most significant activity occurs: the rocky planets, most moons, the asteroid belt, and regions where life might potentially arise. Such a surveyor probe would naturally follow this geometric path. Critics contend that this is a case of selection bias. We are only noticing 3 Atlas because its trajectory brought it close enough for detection. It is plausible that hundreds of interstellar objects traverse the outer solar system on random trajectories, unseen by us due to their extreme distance and faintness. The objects we detect are necessarily those that approach the Sun and Earth. This argument holds validity. Our detection capabilities are heavily skewed towards objects that pass through the inner solar system, where our telescopes are concentrated. We may be missing the vast majority of interstellar visitors that remain in the outer regions. However, this does not explain the specific alignment. Even among objects that pass close to the Sun, most would not be aligned with the ecliptic. The majority would exhibit high inclinations, plunging through the planetary plane at steep angles. The fact that 3 Atlas is nearly coplanar with the planets is unusual, even within the subset of objects detectable by our current technology. Another aspect of the trajectory warrants attention. 3 Atlas is on a hyperbolic orbit with an eccentricity of approximately 6.16. This indicates it is moving well above escape velocity, meaning it is not gravitationally bound to the Sun. It originated from interstellar space and is returning to interstellar space. However, its trajectory can be traced backward. By reversing the orbital mechanics, astronomers can determine its original point of origin. These calculations suggest it originated in the thick disk region of the Milky Way, possibly from a star system 7 to 11 billion years old. This is incredibly ancient, predating our Sun and solar system. If 3 Atlas formed around such an old star, it has been journeying through space for potentially billions of years. Its exposure to cosmic radiation, chemical alterations, and sheer age make it unlike anything previously studied. Its path through the galaxy also provides information. Based on its current velocity, minus the gravitational acceleration from the Sun, 3 Atlas was traveling at approximately 58 kilometers per second through interstellar space before entering our system. This velocity is typical for objects originating from the thick disk population, matching expectations. What does not align is the timing of its arrival. 3 Atlas entered the inner solar system in mid-2025, precisely as our detection capabilities reached a level sufficient for its identification. The Vera C. Rubin Observatory became operational. The Atlas telescope achieved full operational status, and SPAX was launched. All the necessary infrastructure for characterizing an interstellar visitor was in place. Is this a coincidence or a deliberate timing? If an advanced civilization intended to dispatch a probe to survey our system, they might strategically select their arrival time. They might wait until the target civilization has developed sufficient technology to detect and study the probe, arriving when telescopes capable of analyzing composition and measuring trajectories are available. This would represent a form of first contact, when the recipients are equipped to comprehend what they are observing. This scenario sounds like science fiction, but is not entirely implausible. Any civilization capable of interstellar travel would likely possess the means to observe target systems from a distance. They could monitor for technological signatures, such as radio transmissions, artificial lighting, atmospheric pollution, or other indicators that a civilization has reached a particular developmental threshold. Earth has been broadcasting radio signals for over a century. Our technological emanations have been detectable by external observers for decades. If 3 Atlas was dispatched in response to these detected signatures, the timing would be logical. Of course, this premise requires accepting the feasibility of interstellar travel, the capability of a civilization to traverse light years of space, their decision to direct a probe to our location, and their choice to disguise it as a comet. This involves numerous assumptions. However, the trajectory remains highly improbable, a 1 in 500 chance of being perfectly aligned with the planetary plane, with close approaches to multiple worlds, and arriving precisely when we develop the capacity for thorough study. The encounter with Jupiter in March 2026 will be a crucial indicator. If 3 Atlas maintains its predicted trajectory, passing Jupiter at the expected distance without deviation, this would support a natural explanation. Orbits governed purely by gravity are predictable and devoid of surprises. However, if deviations occur, if the trajectory alters in ways not attributable to gravitational perturbations from the planets, then we face a quandary. We would then need to account for what caused the course alteration and natural explanations rapidly become exhausted once gravity and outgassing are ruled out. Chapter 10 addresses the imminent verdict. October 3, 2025, marks a pivotal moment. The high-resolution imaging science experiment, HiRISE, camera will be directed towards 3 Atlas as it passes 29 million kilometers away, providing a resolution of 30 kilometers per pixel. This level of detail should be sufficient to distinguish the nucleus from its dust cloud and to estimate the object's actual size by measuring its surface area. If the nucleus is confirmed to be 5 kilometers in diameter or larger, the statistical improbability becomes virtually impossible to disregard. We should have encountered thousands of smaller interstellar objects before detecting one of this magnitude. The natural explanation would necessitate an ever-increasing number of contrived coincidences. ESA's Mars Express and ExoMars Trace Gas Orbiter will conduct simultaneous observations using spectrometers and cameras, operating across multiple wavelengths with various instruments and from different perspectives. Collectively, these Mars-based spacecraft will provide humanity with the most detailed examination of an interstellar object to date. Additionally, a search will be conducted for precursor probes, objects traveling ahead of 3 Atlas that could reach Mars while the main body is under observation. HiRISE will scan the surrounding space. If any unexpected entities appear, if multiple objects are detected instead of one, the nature of the conversation will immediately shift. Following this, a period of waiting will ensue. 3 Atlas will disappear from Earth's view, passing behind the Sun in late September. We will lose visual contact. The object will reach perihelion, its closest approach to the Sun, on October 30th, obscured from our telescopes by 150 million kilometers of incandescent plasma. This 2-month period of blindness means anything could transpire, unobserved by us. Trajectory adjustments, probe deployments, fragmentation, or any other event occurring during this window will only be learned about in December when the object reemerges. December 3rd is when ground-based telescopes are expected to reacquire 3 Atlas. Amateur astronomers worldwide are making preparations, and professional observatories are scheduling observation time. Every entity desires the first light on the object returning from perihelion. Crucially, everyone will be comparing the post-perihelion observations with the pre-perihelion data. Has its brightness changed? Has its outgassing increased or decreased? Most importantly, is it positioned where calculations predict it should be? If 3 Atlas reappears on a different trajectory, if its orbit has altered in ways inexplicable by gravitational interactions with the Sun and planets, this would constitute evidence of propulsion of technology. At that juncture, even the most skeptical individuals will be compelled to consider alternative explanations. The chemical analysis will also provide further insights. Fresh spectroscopy in December will reveal whether the nickel without iron signature persists, if the carbon dioxide dominance continues, or if new emission lines, absent before perihelion, appear. Thermal processing from solar heating could alter surface chemistry in detectable ways. If the object fragments, this would actually support the natural comet hypothesis. Natural comets occasionally break apart near perihelion due to thermal stress. We have observed this with comets like Shoemaker-Levy 9 before its impact with Jupiter. Fragmentation would be considered normal unless the fragmentation appears controlled. If multiple pieces separate cleanly and head towards distinct destinations, then fragmentation could be interpreted as deployment. The Jupiter encounter in March 2026 is another critical event. NASA's Juno spacecraft, currently in a polar orbit around Jupiter, could potentially observe 3 Atlas as it passes within 54 million kilometers. Juno is equipped with cameras, spectrometers, and particle detectors, instruments designed for studying Jupiter but capable of characterizing this visitor. Discussions have arisen regarding Juno's ability to maneuver for a closer observation. The spacecraft has limited fuel reserves and a predefined mission end. Utilizing that fuel to pursue an interstellar object instead of continuing Jupiter studies would be a controversial decision. However, if the October and December observations reveal something genuinely anomalous, the scientific rationale for redirecting Juno would become compelling. ESA's JUICE spacecraft will also attempt observations in November, though the data transmission will be delayed until February 2026 due to communication constraints. JUICE is positioned further from Earth, on the opposite side of the Sun, utilizing its antenna as a heat shield. Data transmission is restricted until its orientation is adjusted. Consequently, we are accumulating observational data over several months from multiple spacecraft at various locations within the solar system. By the spring of 2026, we will possess the most comprehensive dataset ever compiled for an interstellar object. This dataset will either confirm 3 Atlas as an unusual but naturally occurring comet from another star system, or it will necessitate a serious consideration that we are currently being visited. The scientific community is preparing for both eventualities. Astronomers are privately contemplating the necessary steps should definitive proof of artificial origins emerge. Who makes the official announcement? How can such extraordinary assertions be validated prior to public disclosure? What are the ramifications for planetary defense if additional interstellar objects are detected? A formalized protocol is non-existent, as this scenario was never seriously anticipated. Existing SETI guidelines are primarily geared towards deciphering radio signals and intentional transmissions, not physical entities that resemble comets. The closest existing parallel involves the procedures for confirming extraterrestrial life on Mars or Europa. Rigorous verification, peer evaluation, and multiple independent confirmations before any public statement is issued. However, those protocols presume a time frame of months or even years for analysis. Oumuamua is currently transiting and departing our solar system. To conduct a thorough examination, swift decisions are imperative. A contingent of scientists is proposing an intercept mission. This would involve deploying a small probe to rendezvous with oumuamua before it ventures beyond Jupiter's orbit. The objective would be to capture high-resolution imagery, analyze the expelled gas plume, and measure magnetic fields and particle emissions at close proximity. The critical challenge lies in timing. Even a high-speed spacecraft would require many months to achieve a rendezvous. By the time approval and funding were secured, and by the time the probe was constructed and launched, oumuamua would have long since departed. Interstellar visitors traverse at considerable velocities. Opportunities for observation are measured in weeks, not years. This underscores the significance of the observational window spanning from October through March. This presents our sole opportunity to gather data on the third verified interstellar visitor before it recedes back into the vastness between star systems. Post-March, it will be too distant and too faint for detailed study. We will observe its diminishing presence, meticulously extracting every conceivable piece of information from the observations we manage to acquire, and then we will wait. We will wait to ascertain if our analysis reveals natural explanations for all observed anomalies. We will wait to see if further interstellar objects with comparable characteristics arrive. We will wait to determine if the statistical quandary resolves or intensifies, and we will continue to ponder. Even if the accumulated data ultimately supports a natural origin, and even if every anomaly is accounted for by conventional explanations, we will still wonder. This is because a 60% probability of technological origin inherently implies a 40% probability of a natural occurrence, and 40% is not negligible. The cosmos has a history of surprising us. Consider the discoveries of black holes, dark energy, exoplanets, and gravitational waves. Each revelation unveiled phenomena that were neither predicted nor thoroughly understood. Oumuamua might represent another such surprise, something natural, yet so unusual and unexpected that it compels us to revise our existing models and broaden our comprehension of what is possible. Alternatively, it could signify the most profound discovery in human history. The inaugural confirmed encounter with technology originating from beyond Earth, tangible evidence that we are not solitary, proof that other civilizations exist, and that some among them possess the capability for interstellar travel. The answer will soon be apparent. The data is forthcoming. October 3rd, December 3rd, and March of 2026. 3 dates that hold the potential to fundamentally alter everything.